Hello, everyone, and welcome to another online causal inference seminar. We are very excited today to welcome Ted Westling from the University of Massachusett at Amherst. He's here to present non-parametric tests of the causal null with non-discrete exposures. After Ted's talk, we'll have Oliver Dubsky from the University of Pennsylvania giving the discussion. I'm going to switch over to Chingrong now that we'll be dealing with the Q&A.
Yes, so in case you're not familiar, so please submit your questions in the Q&A box instead of the chat box. So that allows us to keep track of the questions better. So Ted doesn't have a collaborator today to help answering those Q&A live, but you can ask the questions. We may ask you to ask the questions live, in which case we will reach out to you and ask you if you would like us to unmute you. So keep in mind that if you unmute yourself, this talk is being recorded. Without further ado, I will give the stage to Ted.
Okay, let me share my slides. All right, thank you very much for the introduction. Georgia, you did a great job pronouncing Amherst correctly. So congratulations. And thanks for the invitation to speak today in this very nice seminar series. In case you have to leave early or anything like that, I'm just going to give a brief overview of my presentation. So I'll be talking about this paper with the same name as the talk, which is forthcoming in JASA. So it's called Non-Parametric Tests of the Causal Null with Non-Discrete Exposures. And in this paper and in the talk today, we're going to develop non-parametric tests of the null hypothesis that there's no average causal effect of a univariate exposure on an outcome in the vanilla sort of observational causal setting of no unobserved confounding. And perhaps the most novel aspect of these tests is that they permit arbitrary univariate exposures. So the distribution of the exposure, the support of this exposure can be arbitrary in the reals. It can be discrete, continuous, or some mixture of discrete and continuous components. And like the tests in the fully binary setting, our tests are doubly robust consistent, and they have power to detect alternatives that are approaching the null at the rate 1 over root n. So you can find code in R package implementing all of the methods that are in the paper and that I'll talk about today on my GitHub page. So please feel free to download the R package and give it a spin and let me know if you have any issues. So there are 4 parts to my talk today. I'll first talk about, since this is a causal seminar, I'll be careful to carefully frame the causal problem and its identification, the observed data. And then I'll discuss the proposed method, briefly outline the main asymptotic results. And usually I don't present numerical studies or simulation studies in a seminar. It can be a little bit boring, but I think there actually are some interesting aspects of the numerical studies in this paper. So I'll try to highlight them briefly at the end here. And since I don't have someone in the Q&A to help answer questions, I'll try to stop twice after each of these part 1 and part 2, which is where most of the talk will be. So we'll see how we're doing on time. Okay, so let's start with the causal problem and its identification. So I'll use the terms exposure and treatment interchangeably in the talk today, but I'll try to primarily focus on exposure since we'll be in an observational world. So we'll call this exposure capital A. So this is our random exposure of interest, and it's going to live in some set script A. And the only assumption that we're going to make about script A is that it's a subset of the reals. So it's a univariate exposure, but its support, its domain can be arbitrary within the reals and possibly unknown. We don't have to know the support or domain of this exposure before we start. And this is going to be important throughout the talk, so I'll come back to this a couple of times, the role that this support of the exposure plays. And for each possible value of the exposure, so for each element in this support script A, we're going to be working in the potential outcomes framework. So we imagine that we have an outcome that would be observed if we could assign a unit to that value of exposure. So Y of A denotes the potential outcome, and we're going to assume again that it's real value. So it's just a univariate potential outcome. Of course, in causal inference, it's important to specify what the intervention is that we're interested in. And here it's going to be, in a sense, the simplest possible intervention. So we're going to be thinking about assigning all units in the population to exposure value little a. And we think about this intervention again for every possible a in the support of the exposure. Now we can define our counterfactual mean. This is the causal parameter that we'll be focusing on. So the counterfactual mean, which we'll call M of A, is the average value of the potential outcomes over the study population of interest. So this is the average outcome if all units had been possibly counter to fact assigned to exposure value little a. So this is called the counterfactual mean. And this function M, so the function from the domain of the exposure A to the reals, is often called the causal dose response curve, or sometimes alternatively the average dose response function. And typically this terminology is used when the exposure is continuous, but I think we can use it equally well when the exposure takes on some arbitrary values in some set A. Finally, of course, the fundamental problem of causal inference is that we don't get to observe all of these potential outcomes. We imagine them, they live in our heads, but not in the real world. So instead, we only get to observe the observed outcome, what we'll call the observed outcome y, which we will assume to be the potential outcome evaluated at the observed exposure capital A. And this is an assumption in causal inference that this is our observed exposure, known as consistency, not to be confused with statistical consistency of an estimator. And in addition to this observed exposure, we get, observed outcome, we get to see the exposure actually received by a unit and a vector of pre-exposure covariates, which we'll call W. So this is our data unit, and we will be in the simple IID setting where we observe n IID observations of this data unit, and we'll call their unknown distribution P0. So throughout the talk, parameters or functions indexed by 0 will mean that it depends on the unknown distribution P0 that's generating the observed data. All right, so now we have our causal setting, and we can specify what it is that we're actually interested in doing with this causal data. So throughout the talk, we're going to be interested in testing the null hypothesis, which we'll call H0, that the counterfactual means are all the same for every value of A in the support of the exposure. So the M of A, the expected value of Y of A is constant. Versus, we want to test this null hypothesis versus the complementary alternative that the counterfactual means differ for at least two values in the support of the exposure. A couple other ways that we can interpret this null hypothesis. First of all, we can interpret it as the average outcome under assigning all units to exposure value little a. That the average value under this intervention doesn't depend on what value in the exposure we're assigning units to. Alternatively, if you think about this causal parameter, the causal dose response curve on this set A as a curve, then the null hypothesis is that M is flat on the support of the exposure. So here's our function M, and the null hypothesis says that it's a flat function. A little bit more loosely speaking, we can perhaps interpret this null hypothesis as saying that there's no average causal effect of A on Y. Although again, that's a little bit loose when the support A of the exposure is not just binary. There's maybe multiple possible ways you could think about average causal effect, but I think loosely speaking, that's roughly what the null hypothesis says. Okay. So now we've defined our causal setting and what we aim to test, the null hypothesis that we aim to test. But of course, we can't just test this null hypothesis in the observed data without making some assumptions. We call these identifying assumptions in the causal world. So we'll be working, as I mentioned at the beginning, in the vanilla observational data situation of no unobserved confounding. So we're going to assume that the stable unit treatment value holds, so there's no interference or spillover or anything like that. And this no unobserved confounding assumption. So the potential outcome Y of A is conditionally independent of the observed exposure A, given this vector of covariates W. So we're assuming that the observed covariates W are enough to remove confounding between the outcome and the exposure. And in addition, we assume positivity. So roughly speaking, for every unit defined by strata of W, this unit has some chance of receiving exposure value little a. Now, exactly what P is might depend on whether the exposure is discrete or continuous at A. So if it's discrete, then this P should be interpreted as a conditional probability. If it's continuous, then it's a conditional density. But the basic idea is that A is in the conditional support of this distribution of A given W. So if these conditions hold, then the very famous, well-known G formula, also known as a backdoor formula or standardization formula, holds. So we can identify this counterfactual mean parameter with the G formula. So we'll call this theta 0 of A, and it's defined as the expectation of this outcome regression. So here, mu 0 of AW is the conditional mean, the outcome regression of the observed Y on A and W. And in this G formula, we are taking the expectation over the marginal distribution of the covariates W. So this probably looks familiar to many of you in causal inference, that we can identify the counterfactual mean with this G formula. And using this identification, we then have an equivalence of our null hypothesis stated in causal terms in terms of the observed data distribution. So in terms of the observed data, our causal null hypothesis H0 holds if and only if this theta 0, this G computed regression function, is constant on the support of A. And it's constant on the support of A if and only if it's equal to its average value. So this little gamma 0 is the average value of the dose response function over the marginal distribution of the exposure A. And the alternative, the complementary alternative, holds if and only if this dose response function, or this G computed regression function, is not equal to its average for some A in the support of the exposure. So now we've identified our causal problem using the observed data, and we can do statistics. Our statistical goal is to develop a non-parametric test of this null hypothesis versus the alternative. Non-parametric, the simplest explanation for why I'm interested in a non-parametric test is because my work is primarily focused in non-parametric. So I try to be as non-parametric as possible when I can. So I focus on non-parametric estimation and inference, and that's what we'll be focusing on today is developing a non-parametric test. All right, so I also want to mention this strong null hypothesis, which is a little bit different, but related to our goal. So here's our null hypothesis in terms of the observed data distribution. So the null that the G computed regression function is constant on the support of the exposure. Whoops, I seem to have jumped back a long ways. Apologies. Let me jump forward. But there's a stronger null hypothesis that implies our null of interest. So in particular, this null holds if the outcome regression function mu0 doesn't depend on A. So if mu0 of AW is equal to just some function of W with probability 1. And this stronger null can be interpreted as there being no causal effect of A for any unit defined by strata of the covariate W. This is an equally valid null hypothesis to test, but it is different than our null hypothesis. In particular, our null can hold when the strong null does not. So it can be the case that the outcome regression does depend on A, but essentially it averages out over W to still be constant as a function of A. So we're interested in testing this slightly weaker null hypothesis that the average average dose response function essentially is constant. Okay, so I'll pause here briefly in case there are any questions before we move forward to the proposed method.
We don't have any questions so far, Ted, so please go ahead.
Okay. All right. So here again is our null hypothesis stated in terms of the observed data distribution. And you might think, just looking at this null hypothesis, that the support, this script A, this set that the exposure lives on, would determine how we would approach testing this null hypothesis. So in particular, in the case of a binary exposure where this script A is just 0 or 1, well, there are a lot of existing approaches to testing the null hypothesis in this setting. So in particular, the most famous non-parametric methods in this case are augmented IPTW and TMLE. Of course, there are others, so if I'm not mentioning your favorite method, I apologize. But the point is that there's many approaches that we can use in this setting. We can use AIPTW or TMLE to estimate each of the counterfactual means under 0 and under 1, and then test that the two means are equal. These methods can be extended to the situation where the support of the exposure is some finite discrete set. So in this case, we can extend augmented IPTW and TMLE to test the null hypothesis in this case by estimating the counterfactual mean for each value, each unique value in the support of the exposure. And then we would have an asymptotic multivariate normal distribution that we can use to construct a chi-square test of the null hypothesis. However, I want to emphasize that the asymptotics of these tests are, to my knowledge, only valid for fixed k, so for a fixed number of unique values of the exposure. And as we'll see in numerical studies, they actually don't work very well when unless k is much smaller than n. If there are roughly proportional number of unique values to the size of the data, to the number of observations, then these tests don't work so well. So there's motivation, even in this setting, to develop an alternative test. Finally, if the exposure is continuous, well, then you might think, well, we really need a different approach to testing in this situation. And to my knowledge, there doesn't yet exist a test in this continuous exposure setting. There have been a couple of methods proposed, non-parametric methods for estimating the average dose response function in this continuous exposure setting, and for conducting pointwise inference for the causal dose response curve theta 0, but I don't think that that global inference in this continuous exposure setting has been considered. I also want to mention probably the most common approach to dealing with a complicated exposure, an exposure that's possibly continuous or has many levels, which is simply to discretize the exposure. So if it has many levels, maybe make the number of levels smaller, either dichotomize it or trichotomize it or something based on some empirical quantiles or something like that. But I think this is less than ideal for a few reasons. First of all, it's been well documented in the literature that discretizing throws away information. And in the context of testing, this results in a loss of power. Also, there are many possible ways to discretize. It usually isn't really clear a priori what the best choice is. The best choice will probably depend on the true shape of the dose response function, as we'll see in numerical studies. If you want to be powered against all alternatives, you have to be careful about how you discretize. So it can be difficult to know what the best way is. And perhaps also concerning is the possibility that practitioners will possibly choose a discretization based on the results of the analysis. I mean, I hope people aren't doing that, but possibly without realizing it or subconsciously that could be happening. And finally, the causal parameter has a complicated interpretation when the exposure is discretized. Although for the purpose of testing, perhaps we don't actually, that doesn't matter so much. If we're just interested in testing the null, then we can discretize and we're still fine. But nevertheless, I hope you agree that discretization is more a choice or an approach based on convenience, or simply not really knowing how to treat the exposure in its natural undiscretized form, rather than a principled choice to analyzing the data. So all of this is leading up to the point that we want to develop tests that work for all univariate exposures. We want to be robust, essentially, against the form of the marginal distribution of the exposure A. So we don't want to have to think about what the form of the distribution is when we're constructing our test. We don't have to worry that the exposure has too many levels, or is it actually discrete, or is it actually continuous? And I think this is important, especially in observational studies, because some exposures might not actually be fully discrete or fully continuous. Their form is can be a little bit nebulous. So here's an example. We can consider, so we looked at the distribution of this exposure defined as the average number of cigarettes smoked during pregnancy per week during pregnancy among smokers from the CDC data for Pennsylvania in 2004. So this is an exposure that you might be interested in for its effects down the line on health outcomes or birth outcomes. And here is the empirical CDF of this exposure over, I think it's about 20,000 observations. And there's a couple of things I'll point out about this empirical distribution. First of all, it has a lot of levels. I think there's about 100 or something like that, 150, somewhere in there, unique values of the exposure. So it's a little bit hard to know what to do with that right away. And there's as few as one observation per level of the exposure. But on the other hand, there are clearly some fairly large jumps in the distribution of the exposure here. So there's jumps at 10 reported average cigarette smoke per day, and at 5, and maybe at 15, and several other kind of round values. And so it's not really clear, I think, from this CDF what form this distribution has. Should we treat it as fully discrete? Well, that might be a little bit difficult because there's some observations, there's some values of the exposure that have just one observation. So it's hard to know what to do with those. But it isn't really purely continuous either, because it clearly has these jumps. So the point is that I think there's good reason to try to construct tests and procedures that don't rely heavily on the form of this marginal distribution of the exposure. All right, so before I get to defining our test and actually laying out what it is, it's a little bit complicated. It's perhaps not super intuitive without an analogy. So I'm going to develop this analogy here that I think will be useful in motivating the construction of our test. So the analogy I want you to think about is that of testing this very simple null hypothesis that a density function, which we call G0, is flat on the unit interval. So say we're just in the non-causal setting, we're just observing observations on the unit interval, and we want to test whether their density is flat, whether they come from a uniform distribution. Well, one approach to testing this null would be to estimate the density function using, for instance, kernel density estimator or something like that, and then construct a test statistic using that estimator. So using GN, our estimator, construct some test statistic whose distribution under the null we know, or at least whose asymptotic distribution we know under the null, or we can derive under the null, and then use that to construct a test in the usual manner. But estimating a density is hard, not impossible, but kernel density estimators are, their asymptotics are kind of complicated, and their behavior is a little bit complicated, depends strongly on the smoothness of the density and so on. It's a lot easier, I think you'll agree, to estimate the cumulative distribution function, let's call it capital G0. It's easier to estimate this CDF than it is to estimate the density. You can just use the empirical CDF. And furthermore, the null hypothesis that the density is flat on 0 to 1 holds if and only if this alternative null hypothesis holds, if and only if the CDF is equal to X on 0 to 1. So since we can formulate our null hypothesis in terms of this easier to estimate parameter, the CDF, we can then estimate this CDF in an easier way, and it provides us a much simpler method of constructing a test, which leads to the Kolmogorov-Smirnov or Anderson-Darling tests, well known in classical statistics. The analogy in our setting is that estimating theta 0, the dose response function, is challenging when there's many levels of the exposure, especially if the exposure is fully continuous. So instead, we can make the problem easier by, just like with the density, by taking a primitive or an integral transformation of theta 0. That and this transformation will be easier to estimate using essentially very standard non-parametric, semi-parametric methods. It'll be a little bit harder than estimating the CDF because there's nuisance parameters involved. We're in this more difficult causal setting. But nevertheless, the idea is basically the same. We're going to make the problem easier for ourselves by using a primitive transformation. So in order to define this primitive transformation, I need a little bit of definitions, mathematical definitions. So we define F0 as the cumulative distribution, the marginal cumulative distribution of the observed exposure A. We've already defined this gamma 0 as the average over the marginal distribution of A of the dose response function. And we define this capital gamma 0 as the partial average up to A of theta 0. And then finally, we can define this omega 0 as the difference of capital gamma 0 and little gamma 0 times F0. So if you're not following all of this notation, that's okay. The key point is with these definitions, we have the following key results. as long as theta is continuous on the support of the exposure script A, then our null hypothesis holds. So this is the null that we're interested in. This null hypothesis holds if and only if this alternative null holds, that omega 0 defined here is 0 on the entire support of the exposure. So this is like the equivalence between testing that a density function is flat and testing that the CDF corresponding to the density is linear. We've now translated this problem in terms of a hard parameter, theta 0, into an easier parameter, omega 0. And the key here is that unlike theta 0 in the setting of a continuous exposure, omega 0 is pathwise differentiable relative to the nonparametric model at each A, regardless of the form of the exposure, regardless of the distribution F0. We can estimate its influence function and then use standard approaches from semi-parametric and nonparametric statistics to construct what we call a uniformly asymptotically linear estimator of omega 0. And then we can use the asymptotic properties of this estimator to construct a test of the null hypothesis using this key equivalence. So that's really the main idea behind the test. And I don't have full time to describe everything in detail here, but I at least want to lay out the basics of the test. So first of all, we have to choose a p. It can be anything between 1 and infinity. And then we propose the following test of the null hypothesis. First, we have to derive and then estimate the efficient influence function of omega 0. So again, all the details can be found in the paper of the form of the influence function. I don't want to bore you with influence functions on these slides. I can show them at the end if people are interested. I do have slides on them. And in particular, we suggest constructing a cross-fitted one-step estimator omega n of omega 0. So the cross-fitting, or also known as sample splitting or double machine learning, this has become quite popular in the past decade or so as a way to avoid strong empirical process assumptions. So we do have nuisance parameters that we have to estimate. And by cross-fitting, we can avoid restrictions on the complexity of these nuisance estimators. So in particular, we need to estimate the outcome regression, mu0, which we've defined previously. And more difficult is we need an estimator Gn of a version of the propensity score. So this is very common in non-parametric causal inference, that you need estimators of both the outcome regression and the propensity score. The form of the propensity score depends a little bit on the setting. And in this case, because we want to allow both hybrid discrete and continuous exposures, we need to consider this hybrid propensity score, hybrid standardized propensity score. So here G0, this hybrid standardized propensity score, is defined as the usual propensity, the probability that A is equal to A given W is equal to W, divided by the marginal probability that A is A. So this is the usual standardized propensity in cases where A is the probability of observing value little a is positive. And if at points of absolute continuity of the distribution, it's the conditional density divided by the marginal density. So this is a little bit of a price we pay for trying to be flexible about the form of the marginal distribution of the exposure. I'm not sure that there's a way around it. Perhaps there is. We do have a proposed non-parametric estimator that's implemented in the R package. I don't have time to fully get into how we define this estimator. It's kind of based on a copular version of this hybrid standardized propensity score. But I think there's certainly open work to be done in estimating, developing flexible estimators of these types of objects. Okay, once we have our cross-fitted one-step estimator, we can use asymptotic properties of root n times omega n minus omega 0. So under sort of standard doubly robust conditions, root n times omega n minus omega 0 is converging weakly to a Gaussian process. So we can estimate this limiting Gaussian process. It depends on the influence function, so we can plug in the estimated influence functions, and then we can get an approximation, which we'll call TNP alpha, of the appropriate quantile, depending on the level of test we want to perform, of this limiting distribution. So again, this is all fairly standard non-parametric techniques in doubly robust causal inference. And finally, under the null hypothesis, omega 0 is 0, right? That was a key point in our equivalence proposition of the two null hypotheses. So under the null hypothesis of this test statistic, we show that this test statistic is converging in distribution to the appropriate norm of the limiting Gaussian process. So we can compare this test statistic to our estimated quantile of the asymptotic distribution, and reject if the test statistic is larger. So it's kind of a standard. I mean, it's a little bit more complicated because there's more difficult parameters in here, et cetera, but it's essentially a standard approach to testing once we make this equivalence. We find a test statistic whose asymptotic distribution we can approximate, and then we do so. We approximate it and then reject if our test statistic is larger than that approximate quantile. Okay, so before I move on to describing the asymptotic properties of the procedure, I want to briefly pause here again in case there are any questions.
So Ted, we don't have any question at the moment, but let's give our audience a minute to type in their question.
Okay,
I have
good.
a question actually myself
Sure.
about that cigarette smoking example you give us. So that the thing you mentioned about a spike on the round numbers like 5 and 10, that feels more like a measurement error problem to me.
It's a good point. Yeah.
Yeah.
It could be.
Yeah.
Right. Yeah. So the idea being that the actual exposure is some real number, and then people are reporting some rounded version of their real exposure. Yeah, that's a great point. I mean, I think it could be a mix of that and the fact that people might actually sort of tend to smoke a round number of cigarettes per day. I'm not sure exactly how many are in a pack, but that could also be part of the problem. But yeah, so I think.
My question is your test actually robust to this kind of measurement error? Because in some sense, you're testing an independence or a conditional independence, isn't it? So
yeah, I don't know. That's a good question. I haven't thought about what would happen in the context of measurement error. We are, to be clear, in our causal conditions, we're assuming that that there's not measurement error, that we're observing the actual value of the exposure. If there were measurement error, of course, you would have to assume a particular form for it and then develop a different procedure. And I'm not sure whether using our test would yield would have valid properties under that sort of situation.
Okay, thanks for that. And we do got one question from Lucas Godoy-Barraza. So the question is, if it requires a model for the outcome and a model for the propensity, why is it non-parametric? Do you mean these because these models are flexible? Is that what you mean by non-parametric?
Yeah, so it doesn't require models necessarily. It requires estimators, and those estimators can be flexible. So they can be arbitrary estimators. Our asymptotic results, as we'll see, will require will depend on the properties, the asymptotic properties of the estimators. But the estimators themselves can be arbitrary. They can be based on parametric models or based on non-parametric procedures. So I wouldn't say that we require models for the outcome and the propensity. We require estimators for them. Whether those estimators are based on models, they could be, or they could be based on other kinds of more flexible data adaptive estimators. Okay.
And one more question before we move on. This is from an anonymous attendee. So the question is, so in a clinical test setting, so it's possible that there's a lower limit for detection. So basically the exposure is discrete up until some lower limit of detection and then continuous afterwards. Could you discuss the impact here?
Yeah, that's a good question. I mean, I think this approach could be used to test the null hypothesis in that setting where there's a discrete point and then continuous after the lower limit of detection. But again, that's assuming that the lower limit, that this isn't another measurement error issue, that the lower limit of detection is not just that essentially if we're observing below some value, then we observe 0 instead. And in that case, again, I would come back to my earlier answer that I'm not exactly sure what the properties of the test would be if there is a sort of measurement error issue like that. But if that's truly the value of the exposure that you want to test for, then I think that's a good use case for this type of test, where we don't have to assume, we don't have to discretize it, we don't have to think that hard about what the form of the exposure is.
Great. So just one more question, but I think we should let Ted finish his talk first. And if we have time before Oliver's discussion, we'll come back to more questions.
Okay. So thank you very much for the questions. So there's three asymptotic properties of the test that I want to briefly outline. So first is doubly robust consistency. So you may be familiar with doubly robust consistency of an estimator. If you think back to your statistical theory classes, consistency of a test usually means that the power of the test is converging to 1 for a fixed alternative. So that's what we mean by consistency in this context of a test. So in particular, if either the outcome regression or the generalized propensity score is estimated consistently, a very common doubly robust criteria, then the power of our test converges to 1 for any fixed alternative. Alternatively, you can think of it as the type 2 error of the test is converging to 0. So the fact that we can misspecify either the outcome regression or the generalized propensity, or have an inconsistent estimator of one of them, and still attain asymptotic, we can still get a consistent test, still get power converging to 1. That's what we mean by doubly robustness. The second important asymptotic result concerns the correct asymptotic size of the test. So you may be familiar with a condition like this, again, from standard theory for doubly robust estimators. So in particular, if the product of the rates of convergence of our outcome regression estimator and our propensity estimator is faster than 1/√n, and some additional regularity conditions hold, then the asymptotic size of our test it's converging to alpha for any null hypothesis. So for any fixed null hypothesis, we have correct asymptotic size. And so this is what I mean by the test being non-parametric. We don't have specific requirements for the models, and we just attaining correct asymptotic size depends on the rate of convergence of these nuisance estimators, which will of course depend on whether you whether you adopt estimators that are converging fast enough, perhaps are based on correctly specified semi-parametric or parametric models, depends on the number of continuous covariates and so on, in a way that is very common for doubly robust estimators. And the last asymptotic result we have is the power under local alternatives. So the idea with local alternatives in testing is essentially it's one way of characterizing the rate of convergence of the test. It's an attempt to describe the types of local alternatives or alternatives near a null hypothesis that we can still detect. How close can you be to the null and still have power to detect that type of alternative? And the key with this type of local alternative is the rate of convergence here, which in our case is √n. So we're able to detect alternatives in a √n neighborhood, or 1/√n neighborhood of the null. So if we have data for each n, if we have data coming from a local alternative satisfying this condition here, and p0 is such that the null hypothesis holds, and again, additional regularity conditions hold, then the asymptotic power of the test under these local alternatives is non-trivial. It's greater than alpha. So this says that we have non-trivial asymptotic power against local alternatives approaching the null at the rate 1/√n, which is perhaps surprising since when the exposure is discrete, the dose response curve is not pointwise estimable at the rate 1/√n in a non-parametric model. But perhaps not surprising if you think about the fact that our null hypothesis is a global null hypothesis. It's not really related to, or it's not just determined by the pointwise behavior of this dose response function. It has to do with the global behavior of this function, or the global properties of the function. I forgot to mention as well in the previous slide that the regularity conditions here, so they're primarily concerned with boundedness of the nuisance parameters, but in particular, they don't require the nuisance parameters to be in Donsker classes. They don't require these so-called empirical process conditions due to the cross-fitting of the primitive estimator. Okay, and the last section of the talk is some numerical studies. So there's two sets of numerical studies that I want to show you today. In this first numerical study, we consider a mixed continuous discrete exposure, which will we have the true exposure is a mixed continuous discrete exposure, but we discretize it. So we consider using our method with the real exposure, but we also consider using TMLE with the discretization. So we define A0 as the indicator that the true exposure is greater than or equal to 0. We compare the properties of our method to TMLE with this dichotomized exposure. Consider 4 types of alternatives. So increasing in strength linear alternatives, so where theta 0 is linear with an increasing slope, and a quadratic alternative where theta 0 is quadratic, centered around the origin. And we consider 2 nulls, the weak null where theta 0 is flat, but the outcome regression does depend on A, and a strong null where the outcome regression doesn't depend on A. So here's the the empirical type 1 error rate as a function of sample size and for 3 choices of P for our method with cross-fitting, our method without cross-fitting, and TMLE with cross-fitting. So our method with cross-fitting attains very good type 1 error, and we can also see the effect of cross-fitting, especially in smaller samples. So cross-fitting helps reduce this finite sample bias due to the empirical process terms that arise when you don't cross-fit. And TMLE, despite the fact that it's based on a dichotomization of the exposure, its type 1 error rate is also very good. So it's within the 95% bounds that we would expect to see if the true type 1 error rate were 0.05. And here are powers under these different alternatives of our method with cross-fitting and TMLE with cross-fitting. We see, first of all, that under the increasing strength linear alternatives, we have increasing power, which makes sense. And our method is a little bit more powerful in these linear alternatives than TMLE, but not substantially, nothing necessarily to write home about. The more dramatic difference is what happens when under this quadratic alternative. Here, TMLE doesn't have good power, and that's intuitively because when the true effect is quadratic and you discretize, you're implicitly taking an average over the 2 regions that you discretize over. So the implied effect that TMLE is working with is really quite small. There is actually an effect, but it's quite small. And so TMLE's power is very low. And that's generally the case when you discretize. There are types of alternatives under which you will have low power. On the other hand, our test, especially in larger sample sizes, attains much better power. And this is the end of the talk, the last part of the talk here is numerical studies in a discrete case. So here we considered simulations where the exposure is fully discrete, and it has K levels where we varied K between 5 and the sample size divided by 2. And we compared our test for this exposure to a chi-square test based on a cross-fitted augmented IPTW. So we estimated the counterfactual mean for each observed unique value in the exposure and used an asymptotic distribution as if the number of levels of the exposure were not increasing with n for AIPTW to construct a chi-square test. But we shouldn't expect this to necessarily work when K is increasing with n, because as I mentioned earlier, the asymptotics of AIPTW are, to my knowledge, only valid for fixed K, not when K grows with n. And indeed, that's what we see. Under both the weak and strong nulls, the augmented IPTW only has valid type 1 error rate when the number of levels of the exposure is quite small and not growing with n. As the ratio between the number of levels of the exposure and the sample size grows, the type 1 error rate of the AIPTW-based test gets quite bad. Whereas, as I've sort of alluded to, our method its type 1 error rate is relatively invariant to the number of levels of the exposure. It works for all of these settings. So I think this is motivation for considering the use of a test like this or this test, even when the exposure is fully discrete, but it has a large number of levels, especially relative to the sample size. And the power of our test does well, especially in large samples with a strong alternative in these cases for all types of exposures. All right, so here's a summary of what I've talked about today. We've defined a test of this weak causal null hypothesis that applies to arbitrary univariate exposures. And the key idea with our test is to base it on a primitive function rather than going after the dose response function itself. And by doing this, we can both be robust to the form of the distribution of the exposure and attain 1/√n rate of convergence of the test. The tests are doubly robust consistent, have asymptotically valid size, as long as the nuisances are converging fast enough. There's a lot of additional material in the paper that I wasn't able to get to, including full details of the testing procedure, regularity conditions, proofs, details of the numerical results, and 2 applications. So the reviewers also didn't like this example using smoking and birth weight. So we have an example that's actually in the paper of the effect of BMI on immune response in early phase vaccine trials. And again, there's an R package implementing all of the procedures that it'd be great if you would check out. All right, that's it. And thank you so much for listening.
Thank you, Ted. It was a very clear presentation. So because we don't have much time, I don't want to steal out of Oliver's minutes. So let's switch over to discussion, and then hopefully you'll have a couple minutes to respond afterwards.
Okay, sounds good. I'll stop sharing.
Can you see my screen okay?
Yes.
Okay, well, thank you very much for the invitation to speak. Thanks, Ted, for the really very nice talk and for the helpful discussions on the work during the last week. I should also say thank you to Stijn van Steeland at Ghent University, with whom I've had many conversations on non-discrete exposures in the last year. So I think in causal inference, it's fair to say we often focus on the case where an intervention is dichotomous. So I'm certainly guilty of this, but you can certainly see in many methods papers a sentence like, for simplicity, we consider a binary exposure. But I think there's increasing awareness throughout the community in causal inference that certainly in observational studies, relevant exposures often don't have this sort of neat binary form, and there needs to be more tools available for a wider range of interventions. I think there's also perhaps the concern that by maybe having too narrow a focus on the dichotomous case, this may have led to inappropriate dichotomizations when applying causal methods in applied statistical research. And Ted has given a kind of clear description of the problems associated with dichotomization. So I think non-discrete exposures pose lots of interesting challenges that are both kind of causal inference problems. So how can we define a meaningful causal question or estimand or null hypothesis to test, but also statistical challenges such as how can I get tests or intervals with good properties or that are robust. And as I'll kind of try and describe, there's a little bit of a feedback between these two concerns, but they're also to some extent distinct. So one possible estimand in the context of non-discrete and perhaps specifically continuous exposures is the causal dose response curve. So essentially this is saying, well, how does this counterfactual, mean counterfactual change with different values, fixed values of A? And I think there's been quite a lot of interest in these kind of parameters in the last 10 years or so. And sort of as the field moves towards being more and more sort of assumption lean, there's been more and more kind of use of non-parametric methods in order to estimate the curve. So the goal in Ted's work is to construct a test of the null hypothesis, essentially that the causal dose response curve is flat over the support of A. So in terms of constructing a test, what might we want? Well, ideally we want to control the type 1 error, but we also want non-trivial power to detect both linear alternatives but also a flexible class of nonlinear alternatives. So this is kind of the advantages of using a non-parametric test over, for example, getting a test from a kind of fitting a simple marginal structural model. And there are several kind of challenges to overcome. The first is, as Ted describes, that estimating the causal dose response curve, that the typical non-parametric estimators will tend to have a slower rate of convergence, maybe complicated statistical properties. And the second issue is that compared with the kind of more classical non-parametric testing literature, we now have confounding to think about as well. So Ted's kind of first move is to rephrase the null hypothesis in terms of a restriction on the primitive of the mean counterfactual at fixed A, which can be identified as the quantity on the right-hand side of the equality. Now, the test statistic, so the primitive is a much easier parameter to deal with, and therefore Ted's test statistic is based on the influence function for the primitive parameter under a non-parametric model. Now, I think these two moves lead to a class of tests with some really nice properties. So working with the primitive parameter sort of avoids direct reliance, I should say, on an estimate of the dose response curve, and therefore, and Ted argues that this sort of generalizes the tests to arbitrary types of exposures. Using the influence function sort of facilitates incorporation of data adaptive estimators of the propensity score and the outcome regression. And in sort of one Ted's results, he shows that so long as both nuisance estimators converge at sufficiently fast and using the kind of the rates we usually require in TMLE or double machine learning papers, that Ted's tests are both going to have the type 1 error control, but also they're going to have power to detect local alternatives that shrink to the null at 1 over n to the 1 over root n rate. And I think this is certainly impressive because this is the same rate that we usually want in parametric testing problems. So I think that the statistical properties of the test are certainly very impressive, but I think that the more difficult problem in cases with non-discrete exposures is perhaps identifying the relevant null hypothesis to test. So I think it's for certain discrete exposures, the mean counterfactual at a fixed level of A may represent an intervention that's perhaps very unrealistic or hard to conceptualize, and therefore it may not make sense to base a hypothesis test on this quantity over the entire support of A. So I think some of the papers that have kind of pointed out these problems, they typically give BMI as an example, which is actually one of the examples that Ted focuses on in the paper. So this quantity, the mean counterfactual under a fixed A, it also might be very remote from the observed data that we have in our possession. So it's kind of been discussed that for certain problems, it may be that for certain values of the confounders, when the confounders include lifestyle factors and genetic factors, that it just may not be plausible that someone has a very high or very low BMI values. So in Ted's analysis, when he looked at his BMI and exposure, he didn't seem to run into positivity violations, but I think it's quite easy to imagine settings where there could be quite extreme positivity violations. And this may then result in the test having low power due to the over the support of A, due to the kind of strong extrapolation that's required in order to test the null. So in these kind of more difficult cases, it raises the question of what might be a more relevant or useful null hypothesis to test. So one possibility might be to sort of consider the dose response null again, but over a population that's kind of easier to work with. So one kind of simple strategy might be to average over a weighted population where we weight individuals by the conditional variance of the exposure given the confounders. So what this will tend to do is prioritize strata of individuals where there's most information on the causal dose response curve. So a second approach, which is sort of moving away from looking at fixed interventions would be to consider the shifting interventions, such as what if I increased everyone's BMI by 1 unit? Now, I think that often what confuses me about shift interventions is thinking, well, how much should I consider the shift by? Should it be 1, 2, 3 units? But actually this forms kind of quite a natural basis for hypothesis testing, because one might look at a null like, our null might be, well, a shift of delta has no effect on a mean counterfactual for all delta within a certain interval. And then we of course have the problem of deciding on a relevant interval, but it may be using domain knowledge. There may be interesting data adaptive ways of doing this. So sort of to summarize, I think certainly if the causal null Ted's proposing is appropriate, there's no more excuses, at least for testing, to fall back into using awkward dichotomization. Now, for certain types of non-discrete exposures, maybe particularly continuous exposures, other causal null hypotheses may refer to more realistic interventions, or at least be easier to test. But I think that good tests would no doubt share many of the same properties of the class of tests Ted develops, and they also may involve much of the same machinery and build on the novel ideas in this work. So on that note, I'll stop and hand back to Ted. So thanks again for the nice talk.
All right, Ted, would you like to take a couple of minutes to respond? Thank you, Oliver.
Sure. I think Oliver made really good points. So thank you very much, Oliver. Yeah, I think it's absolutely true that the dose response isn't necessarily the right causal parameter to go after in all settings, especially as the number of unique values of the exposure grows. It becomes more and more questionable whether we're really interested in this intervention that assigns all units to a single value of the exposure. That's something I've been thinking about more recently. I think in some cases you're right that we have interventions with more specific interventions in mind that we can consider, and then there have been some recent works that are very nice, proposing approaches for going after those specific interventions, even when the exposure itself can be quite complicated. This isn't necessarily always the case, though, and I think one thing I do. We might not always have a specific intervention like that in mind. And one thing I like about the dose response curve, despite the fact that I agree that it's, also the positivity conditions are quite strong for it, as you mentioned. And there are weaker ones. I think Dominic has a paper actually on relaxing some of those positivity conditions, even in the context to a different in a different parameter in the context of a continuous exposure. But I do like that the dose response curves gives a sense of the shape of the effect, I guess, meant more qualitatively. We get a sense of, does the effect of the exposure, the causal effect of the exposure on the outcome, does it decrease quickly with the value of the exposure? Does it decrease more slowly, or is it roughly linear? We get a sense of that shape in a way that perhaps we wouldn't if we focus on a specific one number or perhaps a small set of interventions. And now perhaps maybe there are ways that we can consider other interventions with weaker positivity assumptions that still give us a sense of the shape of that effect, or what I'm calling the shape of the effect, which I think is useful for getting a general scientific understanding of how the effect works. But I think regardless, there's a lot to do in the area of continuous non-discrete exposures. It's really only recently coming under more scrutiny and causal inference, and I think that's good news for folks. So if you're interested in doing research in causal inference, I think non-discrete or continuous exposures is a great area to work in, because there's just so much to do.
All right, thank you both. We can talk about a little bit more afterwards. Before you all go, I want to remind you that next week we have another causal inference seminar. We will be welcoming Eugene Lee from Brown University, who will be talking to us about evidence factors from multiple possibly invalid instrumental variables. I hope we see you all there.